We'd like to welcome you to this first in the series of 3 webinars from cybersecurity company Cytel, in which we will be discussing Fuzz testing and its application to smart meters. I'm Rebecca and I will be your host today. Firstly, I want to let you know that this session is being recorded and will be shared with attendees for on-demand viewing, minus the situation at the start of the webinar. In today's session, we'll learn what fuzz testing actually is, why it should be applied to smart meters. The Cytel team will talk you through how it works and why it should be considered as a valuable tool in your cybersecurity toolbox. There will be time at the end of the session for any questions, so please do send them through using the Q&A button at the bottom of your screen. Joining us today from Cytel, we have David, Tony and Chris, all of whom have decades of experience in cybersecurity and are contributors to Cytel's unique fuzz testing tool, Protocrawler. I'll hand over to David to kick off the session and tell us why you should test smart meters.
So thanks, Becky, and thank you for joining. Apologies about that. It's a new platform. We're just getting used to using this here. So I'm going to run through a few of the reasons why we believe fuzz testing of smart metering infrastructure is a good thing to do today. And I'll also describe the rationale for smart metering businesses actually undertaking this type of testing in our own home market in the UK. But these same drivers apply to other markets that we've observed. So with nearly 300 million smart and advanced meters deployed in Europe to date, and with the global market estimated to grow at around about 11% per annum, we can all appreciate why smart operators and asset owners are justified in being concerned about cyber risk. Meter populations of this size provide an attractive attack surface for potential adversaries. So, for example, we have attack scenarios involving state-sponsored actors, terrorists and activists that are typically designed to cause mass disruption to end users, energy networks and asset owners by instigating a coordinated attack on the core infrastructure, including in-premise consumer devices. So, for example, gaining control over load switches and valves to disrupt consumers, cause blackouts, or in extreme circumstances to destabilize the distribution network. The volume and diversity of connected devices make this type of attack increasingly effective. And we've got huge numbers of renewables coming online with new communication standards for things like electric vehicle smart charging and vehicle-to-grid applications. Attack scenarios involving criminal elements tend to involve stealing of sensitive and personal data. And they do this to sell this data onto third parties, possibly state-sponsored, or to extort individuals and organizations. Sensitive data includes cryptographic security credentials, which can be, if acquired, could pose a risk of a secondary exploit of other smart meter communication systems, such as the head-end system or a meter data management system. Individual end users invariably tamper with metering equipment and metering applications to influence metrology or to steal energy. This type of exploit obviously needs to be simple, it needs to be cheap, and it needs to be able to be carried out with limited knowledge. The exploit also needs to be easily shared, so for example, distributing it across the internet. So we're facing a number of challenges, security challenges to overcome here. As mentioned, critical national infrastructure poses a clear target to prevent that, and preventing damage to that infrastructure is more essential given that we all need to help consumers manage escalating energy bills. And indeed, back in 2017, in our own home market, National Grid admitted this much. Deployments at scale include a huge number of dependent connected applications and services that consume this metrology data. And smart meters typically operate in uncontrolled environments. So we simply can't prevent attackers accessing and studying these devices. Most communicate using interoperable standards such as TLMS COSAM, which by their nature do help to reduce the cyber risk. But this means flaws can be shared by an entire asset population, and interpretation of standards can vary by manufacturer and by market. Metering assets have very long lifetimes, typically 10, 15, or even 20 years, and over which time the operator and the vendor are required to maintain compliance to the technical specifications. Software can also present new targets in the future as attackers gain access to more powerful processing, potentially capable of breaking cryptographic protections that are in place today. And deployment of software and firmware updates carry risk, inherent risk, which asset owners are typically don't like to do as a routine activity. And lastly, there's rich connectivity options available to provide multiple access points and portals to other parts of the system. So, for example, upstream data retrieval and data management systems, as mentioned, and downstream applications for distributed energy, for automation, for e-commerce, for security, and so on. So if these large deployments of smart and advanced meters are prime targets for an attack, what are we actually doing about it? Well, most developers that we work with apply fairly robust secure by design principles during R&D. And most national AMI deployments also impose some level of security architecture and controls to protect data, systems, and assets. However, all cybersecurity development processes have a strong emphasis on testing. Traditionally, security functionality and protections are tested using positive tests to demonstrate that a product or system actually does what it's supposed to do. That is, it exhibits the correct security function behavior. In our experience working with developers as a formal certification lab, this is where the majority of the assurance budget goes. Similarly, system developers may undertake different forms of penetration testing and vulnerability analysis. Typically here, they're looking for potential vulnerabilities exposed by previously discovered and established attack vectors. These are usually found from earlier testing or based on specific attacks that have been detailed in a publicly disclosed vulnerability database. And of course, we can also inspect application security by inspecting how the developer actually develops that application, security inherent in the development processes. And we can conduct manual and automated source code analysis. And all of this together is in an attempt to model out the threats that are posed by different attack vectors. And this is typically all about what the system should do. We're more interested today talking about a form of negative testing to find what the device shouldn't do. So one important type of negative testing is fuzz testing. Fuzz testing or fuzzing, as we sometimes refer to it, is done in a very different way to positive functional testing. And it enables us to identify the underlying causes of security vulnerabilities. During fuzzing, we're essentially looking for issues that lead to previously undiscovered vulnerabilities. The technique is commonly used by attackers to discover software and firmware bugs that they can study and then later turn into exploitable vulnerabilities. Attackers tend to have significantly more time on their hands to find these bugs and loopholes in order to develop exploits, but automated testing, and in this case, automated fuzz testing can help you get ahead by embedding testing into your regular software development and testing processes. For this reason, it's best to start testing as early as possible in development. However, as fuzzing tends to also identify the most serious issues relatively early in testing, it's also an effective proof of robustness test for smart meters. And before they deploy these assets into the field, you could invest a significant amount of your time into finding the same issues, but fuzzing will find them much quicker without supervision, and testing can be repeated consistently. And it doesn't just apply to new products. As a lab, we are continually finding issues in mature products that have been in the field for a number of years. So the goal here is to find and fix bugs as early as possible in order to avoid dealing with the consequences and the impact of exploitable vulnerabilities being discovered in the field where they're significantly more costly and challenging to address. So fuzzing requirements are increasingly appearing in metering-related and other relevant standards, recommendations, and legislation. Fuzzing is referenced by name, it might be referenced by name, but if you see any requirements stating input validation or communications robustness or interface robustness, they're basically talking and expecting you to undertake fuzzing. We're now seeing requirements appearing in relevant standards. So, for example, in our own UK market, smart metering cybersecurity requirements explicitly require us to undertake detailed fuzzing and extensive fuzzing on all new products that are going to be placed into the market. And this is where we've gained most of our recent experience testing state-of-the-art products for the UK market. The new YETSI standard for IoT devices requires input validation, as does the de facto standard for industrial control and automation systems, IEC 62443. And there are recommendations abound for highlighting the benefits of example. So in the US, the NIST actually published a recommendation for doing fuzzing in the guidelines for the minimum standards for software verification, and different maturity models and frameworks such as BSIM and others like this are now explicitly requiring fuzzing to be undertaken. And in fact, that last one, BSIM, is actually the recommendation for fuzzing was actually increased in priority, recognizing that fuzzing is becoming a significantly more important practice. And regulations as well are starting to reflect these security requirements. So, for example, in the UK, the telecom strategy requires network vendors to undertake fuzzing, and input validation requirements have recently entered regulations for smart charging of electric vehicles. So if we should be doing fuzzing, where can fuzzing be applied? Well, in short, anywhere really. We can apply fuzzing to any interface within a smart metering architecture. We can fuzz individual interfaces of equipment in the home or in the business process premises. So, for example, in the UK, we fuzz the Zigbee low power radio network interface layer, the upper encapsulation layers, and then the actual application layers themselves, all independently. And these are all defined by the government's technical specifications. We could equally apply fuzzing to assets in the wider communications network. So, for example, upstream communications or data concentrators, like in a PLC or a LoRaWAN network. And in this case, the network topology doesn't matter. As long as we can inject our fuzz messages into the device, we can undertake detailed fuzzing. And we can fuzz interfaces in the back office systems, whether it be the cloud-based or if they're based on actual hardware or software in-premise systems. So I'm going to wind up this part of the webinar, and just to summarize that there are good reasons for undertaking fuzzing of smart metering. It's an effective method to automate continual validation of both development and in developed and in developed devices. So it's never too early to do it, and you want to continue to do this to get the true benefits of it. It's also becoming an accepted good practice. So there are more and more regulation and areas to come, and we're tracking regulations and standards around the globe. And there are more and more regulations appearing every day, asking vendors and requiring them to undertake this type of testing. And it's also capable of finding issues and bugs that other traditional methods of testing normally miss. And it's always much easier to do the testing as a continual activity that is automatable, so you don't require to invest in that expertise and expensive teams to continually undertake this type of detailed testing. So I'm going to pass over to Tony now. We'll try and pick up pace here so we keep to the timeline. Tony's going to take you through some of the details of how fuzzing is actually done in practice. And obviously there are a number of different fuzzers and fuzzing applications that are available in the market. But for the purposes of today, we're just going to focus on our particular brand of fuzzing. the type of fuzzing that we do is a test lab. And then lastly, Chris will take you through an actual practical description of how our actual tool, Protocrawler, undertakes this testing. I should stress that none of the results that we show you today are real. They've all been redacted and sanitized, but they are representational of actual issues that we found in the field with Protocrawler. So on that, I'm going to pass back to Becky.
Thanks, David. So before we start the next section of the webinar, we'd like to run just a quick poll with you. So you should see on your screen, we just want to ask, are you familiar with the concept of fuzzing, and have you conducted fuzzing in some capacity before? So it looks like we've got a bit of a combination of responses to this. Some people who haven't had any previous experience of fuzzing, and some who have it as a core component of their quality assurance. But either way, I think this next section will be helpful for all of our audience today. So I'll now hand over to Tony to tell us how fuzz testing actually works.
Thanks very much, Becky. Yes, I'm going to talk a bit about what fuzz testing actually is, and how you do it, what it involves, and why it works so well. Fuzz testing is something that can appear very simple. From another view, it can appear very complicated, and this is one of the reasons that we wrap up a lot of the experience that we've gained and the best practice that we've worked out into a tool to try and avoid everybody having to recreate this for themselves for the first time. Fundamentally, what fuzz testing is what we have on this slide here. It's about taking a fuzzing tool that you can see on the left and sending massive volumes of malformed messages, malformed inputs to the target under test that's on the right. We then observe the behavior of the target. We capture that behavior so that we can then analyze it. And we're going to be looking for unexpected behavior, things we didn't expect the target to do, or even suspicious things that make us think, oh, there could be a vulnerability, a security issue there. Next slide, please. So one of the things to point out is that fuzz testing, for some of you who may have come across fuzzing before, certainly if it was a while ago, originally fuzzing was pretty much about just sending random data to the target. We would stream a lot of random data, and that did work on old devices. That would be sufficient to crash them, make them fall over. These days, we don't see that. We tend to see more resilient devices to start with. And so we're looking at doing something that's a lot beyond that. There's another notion of fuzzing, which is about capturing real messages that have been sent and then changing them slightly, what we call mutations. And that has a place as well. But because we have things like CRCs or signatures, MACs, things that check the message content, we need to do a lot more than just that. So our approach, what we're going to talk about today, uses automated, intelligent generation of massive numbers of these tests, and then it applies that understanding of the communications protocol, both to generate the messages and to analyze the results. Next slide, please. So we'll start off by thinking about what a malformed message is. I've talked very, very casually about sending malformed messages. I have to give a warning that's on the bottom of this slide that the real situation here is quite a lot more complicated than I'm going to describe here. But this will give you an outline and the general idea of different levels at which we can do malformation. We're going to start off with this generic message that you can see on the screen here, and some of you may even recognize that as pretty closely based on the UK smart metering protocol in GBCS. So you've got different headers, you've got a core payload in there, and then you've got security data at the end in the form of a signature or a MAC or both. So when we talk about sending this to the device, of course, what it ends up with is a lot of hexadecimal bytes, as you can see under the picture there. So the first level we can do malformations at is to say, well, forget about the structure. Just look at that stream. Just maybe replace that whole message with the same number of random bytes. or maybe twice the number of random bytes. This is very close to that old view of fuzzing where we're just sending random data. There's still a place for it. It's just that we have to do more. Other things we can do at this whole message level are maybe to cut off some parts at the beginning or the end of the message. Maybe we take a valid message and we flip some bits, and so on. So these are all things we do without understanding much about the message. We just treat it as a hex string. The next level we can go to is what we call syntax-based malformations. So here you can see we've broken down the payload into something that's a bit more structured, and we end up with fields in the message that have data types. And what we do is we say, well, what can we do with that data type? We start from a valid message, but then we change one of the fields there according to its data type. Maybe in the reading's an integer, so we'll put very large integers or very small integers. The point here is these sometimes get things added to them later, so they overflow, or things like that. With the string that represents the label on the reading, we might put something in there that's valid SQL or a valid URL, because again, these fields get used for other things later in the code. So we're investigating things like that just based on the data type. Next slide, please. So the third level we can go to is the semantic malformations. So this is where we still have the same message. We're looking at this same breakdown of the payload, but we're saying, what do we know about the tag? What do we know about the length? What do we know about the value? The tag is probably going to be one of a number of values in a space. Let's say it's 2 bytes. Not all of those 2-byte values are going to be used, so we'll try all of those values that aren't used. The length is important because it's not just a number, it represents the number of bytes in the next field. So what if we break that constraint? What if we make it different? The value itself, in this case, we've got it as a timestamp. What if we put in something that's a far future date? What if we put in something that's older than this generation of the system? All of those things we can do not only in their own right, but we can vary as to whether the security data on the end is valid or invalid. So we can put in an invalid MAC, which is the easiest thing, where an attacker might just change something and end up with an invalid piece of security data. Or we can do something that simulates more of, say, an insider view, where we actually put correct security data on the end of it, but fuzzed fields. Next slide, please. So that's some indication of what we do with the malformations. That's really all about the first stage in our model of fuzz testing, which you can see on this next slide. You've got generation. That's basically what we were just doing. You saw the sort of parameters we've got there, but there are other things we can do to configure it, as Chris will show a bit later on, based on how much time you've got available, adapting to different amounts of time if you're running overnight versus if you're doing a ceremonial pre-release test. And we're asking, what depth of coverage do you need? And we're adapting to that. The next stage, we actually take those messages and run them. That's the execution stage. So we're seeing then, we're capturing what the target did. We're capturing other sources of evidence, like maybe logs. Then when we've got that, when we've got all the results, the hundreds of thousands of results, tens of thousands of results, we go to analysis. We can't look at those sorts of numbers of results by eye. We can't do that manually. So again, we need automation. And one of the other things we can do with automation is we can actually score tests. We can look at what they showed and we can give scores for different aspects of what they showed. Again, Chris will show you this a bit later on, but we can end up putting the results into a prioritized order with scores so that you can actually make some judgments about which are important, which you want to start working on and further investigating. The point about analysis is that we are reusing in that analysis, we're reusing understanding of the protocol as well. So we're not just looking for a simple pass-fail or some sort of indicator of error. We're actually looking at an understanding of what a response should look like. So that enriches what we can deduce from it. The final stage we get to is reporting, and that's where we're talking about sharing the results that we've got beyond the team that generate them. So maybe you're giving it to the development team to go work out how to diagnose and fix the bugs. Maybe you're showing it to a risk owner or some other stakeholder to demonstrate the resilience of the product and to show due diligence in your testing. So all of these things will take us outside of the tool view and take us into how can we have something that's shared with other parties. Next slide, please. We talk about analysis, and one of the things that's relatively important to say here is that analysis has moved on as well. In the early days, we would look just for crashes of the target. Now we're asking, again, more intelligent questions, more detailed questions. So we're going to look at things like, did we get any responses that were undecodable, not proper protocol messages? Did we get any where we decoded them, but they were semantically invalid? Did we get the target apparently ignoring a malformation and doing an action? Did we get it ignoring security data? And a series of other questions we can ask. This can also be about finding non-conformances, protocol non-conformances. And so it's another part of using fuzzing for acceptance that can help you find interoperability issues in the product or in the products that it's the other parts of the system that it's going to communicate with. Next slide, please. So one of the questions we are sometimes asked is, and what does it mean if we get nothing? What does it mean if no issues are found? I would have to say, in our experience, you would probably be roughly the first. But in any case, what if that did happen? Well, what you've got there is an active demonstration that your product really is highly resilient, and it takes you beyond saying those words. It means you can demonstrate what you mean by highly resilient with the sort of statistics and graphs that Chris again will show you later. It gives you a way of creating a visible metric of your thoroughness of testing. It also means that if you continue to test and you use the fuzzing as a regression test, again, you can show that over time you are maybe improving, reducing the number of issues, or you can show in a regression sense that previous issues haven't been reintroduced. Next slide, please. So the final thing I'm going to say is to sum up why this makes for an effective test approach. The first point is that fuzzing is black box. It means you don't have to start using information that you may not have if it's a third-party device or a third-party component about the design or the source code. If you have that information, you can actually use that to help in generation and in analysis, but you don't need it. The next 2 points are related. They're about automation. We use automation in the tool set to avoid making assumptions, to avoid unconscious biases or mistaken beliefs that we might have about the other components involved. And testing gives us a consistent and repeatable way of doing large-scale, massive numbers of tests. The tool doesn't get tired. We know this is a general benefit of automation, of course, but you can contrast that with the situation you have if you're trying to generate masses of manually defined tests, or if you're trying to do manual code review, for example. The next things are that fuzzing identifies bugs. It's not agonizing over whether it's a vulnerability. It just identifies a bug to fix. It does this at an early stage. If you're using it in the development lifecycle, then you're catching them when they're easier, quicker, and cheaper to fix. And the thing about bugs versus vulnerabilities is that even bugs that aren't vulnerabilities are worth fixing because they could affect interoperability in the field. And just because we don't think of them as vulnerabilities now doesn't mean a clever attacker over time won't find a way to exploit them. So that's my conclusion. I'm now going to hand back to Becky, I think, for our second polling question.
Thanks, Tony. So before we go into the final section, we would like to run another quick poll with you. So this time we'd like to understand what keeps you awake at night when you're thinking about security risk. So it seems that a number of you are concerned about the robustness of your security, which is an interesting response. So I will hand over to Chris now for the final section of our webinar before we head into the Q&A. So just a quick reminder, if you do have any questions, please do submit them using the button at the bottom of the screen. But Chris, why don't you tell us a bit about how you apply fuzz testing to smart meters?
Thank you, Becky. And yes, good to hear that there's already some keen fuzzers in the webinar and that you're all concerned about this stuff. We do think it's very important. So that's good to hear that others see that as well. Yeah, I'm going to follow on from Tony. Tony's given you a sort of practical idea of or a theoretical idea of how to go about fuzzing and some insight into the principles behind our approach. I'm going to get stuck in and give you some of a feel of what it's like for me when I've been fuzz testing these meters over the last few years, how we go about it with our tool, what it looks like and what we're considering. So I'm going to follow the 4-step process as Tony laid out. We're going to start with some generation, go through some execution of tests, analysis, report. My primary objective, of course, is to find those juicy security vulnerabilities, those bugs, those problems, those weaknesses in the product, or just general instability issues that an attacker might exploit. So that's what I'm looking for. But I have some secondary objectives as well as a tester. I want to understand the level of assurance I'm getting when I'm doing this testing. And I also potentially want to demonstrate that to others, either the problems that I found or the level of robustness I've demonstrated to others. So those are my objectives. Let's get stuck into the tool. Let's actually look at how we go about fuzzing some smart meters. So first up, generation. This is where we're looking to Protocooler use its engine to create very large numbers of test cases. So it's what we're asking it here is to use all its knowledge of the target, all its understanding of the protocols, and its wealth of sort of expertise in what sort of problems, how to trigger problems, what's likely to cause issues, to generate automatically for us a very large number of good quality test data that will maximize our chances of finding problems in the available time. And time is a key concept here because the generation engine is very powerful and it can give you a near infinite number of possible test cases, but I've yet to meet the test engineer that has an infinite amount of time available. So a lot of this stage for me in practice is balancing the assurance I want against the time available. And you can see on screen here what I'm doing, and this is just for a simple UK e-meter, I think, showing me setting protocol of various target numbers of tests for each, and that's me moving the slider at the top to do that. And then for each one of those, protocol is first projecting the amount of time it thinks it will take to execute those tests, given its knowledge of the tests and the target. And then it's projecting for me in the graphs below, all sorts of metrics that are indicating to me the quality of testing it projects that I will achieve from that test count. So to give you a very simple flavor, the graph in the middle is showing the relative intelligence levels of the testing, and you can see that the proportions vary over time. The graphs above that give me indications of the distributions, the types of tests that I'm getting at particular levels, and the chart on the top left is giving me indications of the coverage of the different messages. So there's lots of metrics here, but they're all designed to give me an insight for the breadth and the depth of testing that I'm going to achieve, and I'm trying to match that to my available time and the level of assurance I want to achieve. This is a critical thing actually for metering, because if you're going after the meters in particular, they're not necessarily the fastest devices. And so as Tony said, fuzzing and particularly other people's approaches, fuzzing often leverage scale and just sheer quantity to trigger results. But if your device doesn't respond quickly, you won't have the time to do that. And therefore balancing quantity with intelligence level and quality is of particular importance in the smart metering field, in my experience. So it's extra important, this step. So yeah, that's the key points of what we're covering in generation. And obviously the main thing out of it, we get thousands of these tests, many of them unique, never run before, but all following the specs you just laid out to attack the target and give you the maximum chance of spotting some vulnerabilities. So having generated these tests in the tool, we have to run them, which we'll see on the next slide. I'm not going to describe this in general. You can see me here executing a simple set of tests against, I think, a DLMS COSEM meter protocol, run them. There's quite a lot to say about it, gathers all sorts of evidence when it's running, and we'll use that later. But we're going to come back to this step in later webinars. So for now, I'm just going to say, we run them, we get some evidence. So if David moves on, and then you'll remember the third step in our process is analysis. So we having executed all this high quality test data and gathered all the evidence of what's happened, what we really want to do now is find those results. That's what we came here for. And obviously, we don't want as a human to be reading thousands of tests and trying to manually do that. So what I'm doing here is asking Protocaller to analyze a whole set of tests, and it will use all its knowledge of what could indicate a vulnerability and all the evidence that it's seen to ask the sort of questions that Tony alluded to earlier of the test data, and start calling my attention to potential areas of interest and results. And they kind of break down into two sort of main things that I looked for, to be honest, when I'm running. So on the next slide, we can see some overview statistics. So if you go back to generation, you'll know that Protocol was projecting the level of testing that it anticipated in breadth of coverage, breadth and depth coverage. Now we have real results, so I often want to check that I did achieve what I was setting out and projected to achieve. And then on the next slide, we get to the real stuff, which is results. So as Tony has said, well, the key problem with fuzzing, or one of the key problems in fuzzing, is you got all of this test data, but you don't have time to go through it manually. You want your attention called to the things of most interest. We, with Protocaller, have a scoring system to achieve that. So each test is assigned a score. And that score is built up of various components where Protocaller has looked at it and decided how interesting Protocaller thinks it is. And obviously with that, you can then get a prioritized list, which is essentially telling you, this is what Protocaller thinks is most interesting and where you should spend your time investigating problems. And it's not just a number, it's made up of components, so you can understand the basis on which Protocaller is flagging that to you. And that's what I would do at this stage. So that's analysis in a nutshell, and what you get is these nice set of results which are useful for debugging things but are also comparable. So often we you might want to compare how this version of the product did against previous versions, and obviously we're hoping to see improvement over time in terms of security and robustness, and that will come through in these scores and these results. And you can also do it as a comparison. So you can tell Protocol to run similar sets of tests against different products and use the analysis scores and results as a comparison mechanism to compare their security and their robustness. So that's what we're trying to go. And the metering, it's particularly good because there's all sorts of interesting data points that meters give you, which can be fed into the analysis. So we get much more than the basic logs that we might get in a software product. There's much more to pull in. Finally, you've got all these nice results, and you want to go show them to people. Very often, this might sound like reporting might seem like a very basic concept, but actually we found people really like the fact that Protocol will let you export various levels of detailed reports and share them with people who don't have Protocaller. So you can see here, this is just an example template of stuff we do in one of the certification schemes that we provide to the as part of evidence in that, but they're highly customizable. And you can include all the good stuff that you've seen before, but just in an easy HTML browsable form. So if we skip forward a slide, we'll see you can get test distribution statistics, giving you that same coverage stuff we were talking about, which this is a simple example. If we skip forward, you can choose to include all the detailed information of packet traces, logs, evidence, so you can give that to your engineers and have that there for them to browse. They don't necessarily need to Protocol or understand how it works. They have all the evidence of what it thought the problem was to hand in this form. And then, of course, on the next slide, we include the details of the results, of which you can see an indicative mock-up of one here, which is the same thing you saw in the score table, but it's exported. So the reporting is actually simple but very powerful. And we've seen that actually, I'll say the smart metering community is quite good with us. We've done quite a lot of testing with it, and there does seem to be a lot of desire to share these reports with third parties in the metering space, whether that be because there's accreditation requirements or because customers want some sort of evidence of the security and the robustness of the product, and this is an easy way to show. Yeah, we cover that. So that, in a nutshell, is the a very whistle-stop tour of me going and testing some meters with Protocrawler. We are going to expand on it in future webinars, but it will give you a feel. And I'm going to hand back to Becky, who I think will take your questions.
Thanks, Chris. And thank you to David and Tony also for their insightful contributions to today's webinar session. There's clearly a lot more to learn about fuzz testing smart meters, but I hope today's mere scratch at the surface has given you a good understanding of fuzz testing as a cybersecurity tool. So I appreciate we're running over time slightly, but we do have some time to take your questions. We've had a couple come in, so I'll kick off with the first, which asks, given the infeasibly large number of possible maltest inputs, how do you relate the number of or type of tests performed against confidence in security posture? I'll ask Tony, maybe if you can jump in and answer that one for us.
Yes, well, I can try. So I suspect anybody who asks that question already knows how hard it is to get a relationship between the techniques you apply in development and the assurance result, or the confidence in your security posture, as it was put. I think we've wrestled with this throughout my career in cybersecurity, which is several tens of years, and we don't have great metrics. We have things like assurance levels in some of the cybersecurity evaluation schemes and that, but we're really, we have notions like attack potential, but we're really kind of short of metrics. One of the things we like about doing fuzzing the way we've described is you do get abilities to make some sort of measure. So, for example, we can say, as Chris was showing, we can present graphs. Those graphs show things like percentages of the available message space that you cover. You can use that if you have a particular interest. If we know, for example, that certain messages are much more important to security than others, we can show that we concentrate on those. As the question says, there are massive numbers. We aren't going to test every possibility, but we can at least show that the proportions of our tests are focusing more highly on, say, the security fields, or the types of messages that carry out security actions. Or another thing we sometimes talk about is paying most attention to the fields that are processed before you've authenticated. So after you've authenticated, you've got some idea that the person is trustworthy. We don't necessarily stop there and say, oh, well, that's fine then. But we can maybe load our testing towards saying, well, we really want to look more at the things that come in before, that we process before authentication. So these are all things that we can express through some of the graphs and some of the reporting statistics that Chris was talking about. And there are more pages in the report and the analysis that we didn't have time to show here. That if people are interested, we can show in more focused demonstrations. But hopefully that answers the first question as best as we can.
Thank you, Tony. I mean, Chris, did you have anything else you'd like to input on that?
No, I think Tony did it. It's a hard problem, but I think we can leverage Protocrawler. The only thing I'd add as well is Protocrawler has an understanding of where parts of the protocol that might cause problems or things that are strong indicators of issues. And as Tony was saying, it can present the graphs that show you that it's hitting the most high-risk areas and what level of coverage and what depth of coverage you're getting from that. And so that gives you confidence. It gives you increased confidence. It doesn't give you certainty, because we can't, unless you can cover the entire space, you can't prove that there isn't something off in the corner, but protocol allows you to focus in on the most high risk areas and then allows you to demonstrate the level of depth and coverage you achieved to show a level of confidence. So that's what I would say.
Great, thank you, Chris. And as a follow-up question, we have also received, what is the cost benefit of the number of tests on the security posture? I don't know, perhaps if we go back to Tony for that one.
Yes, I mean, again, I can take a stab at this. It is. So we always get this question, of course, with security. What's it worth spending? And traditionally, I suppose we answer that with, well, what's the potential cost of an issue that arises? So if we've got something that causes a crash and that comes up as a customer discovery in the field, or worse still, after you've got huge numbers of devices deployed, the cost implication of that is pretty high. It might be that the requirement and therefore the cost is driven by a procurement requirement in the specification of the system, in which case, of course, you have a way of sort of trading off and saying, well, to get that coverage, it will cost this much. I think that the idea that that testing is expensive is something that often comes up because people see it as a thing that's between you and releasing. But I do think what we come back to is, well, consider the reputational, consider the customer impact, consider the national infrastructure potential impacts. So this is never to say you can spend infinite amounts, of course, but it's a pretty high benefit that I would argue you get from this sort of security testing, because we're exploring areas that we know from experience other methods of testing don't find.
So we've had a follow-up question that is, what is the benefit of fuzzing authenticated packets? Would the attacker not require the key material to craft a malicious packet that is accepted by the meter? Who wants to take that one?
Chris, you or I could do that. Do you want to do it?
I'm happy to jump in there. So there could be many benefits. Firstly, you have to decide who your threat actors are and whether you consider that somebody might be able to issue some level of authenticated message. So it's possible that an attacker might have no credentials, but it's also possible that an attacker might get limited credentials and then wish to attack further into the system. So that can be a strong benefit of in those cases. You also have to consider that at what point and how robustly is that authentication checked. And frankly, we see it absolutely all the time that people say to us, only test here because after this point, there's a MAC or there's a signature or there's an authentication step. And honestly, as a test, when I'm doing the testing, I always include some stuff beyond that, because the number of times where somebody at some point made the choice to, we'll just peek into the contents, we'll just look a little bit further, or actually we need to decode further to get to the signature bit, and our ASN1 pass that does that decoding peeks into the data and then has a problem that means that even though it's in a notionally authenticated part of the message or part of the message sequences, actually an unauthenticated attacker can trigger a vulnerability. So there are good reasons to do it, and that goes to a sort of wider thing with fuzzing, which is the tool doesn't make the same assumptions as a human, and in some ways that makes it dumber, but in some ways that makes it better, because it will find these things where people go, oh, it's authenticated, it's okay, and it turns out you're decoding some of it to get the key or something, or to get the signature or something. So it's always worth testing those assumptions as well. So there can be multiple reasons, and I have to say we find vulnerabilities all the time in places where people say, oh, an attacker couldn't get there.
Okay, thank you, Chris. So another question, from your experience, what is the general security posture of the metering device? How many critical findings defects do you discover on average per device?
Should I jump in there again? I suppose I'm best placed
for that one again as well, Chris. Yeah.
I have to say, we have tested a whole range of smart meters in different contexts, and we tend to find a decent number of significant issues in each one. So I don't think we've ever had a meter get through with no issues that a developer hasn't wanted to fix. Exact numbers, it's kind of, that does depend how much testing we've done, but I'd say that we definitely get a range. I will say that we have also done the thing of testing the same meter multiple times and over time, and we have been able to achieve a downward trend and an increase in improvement in the security, a downward trend in the issues and the severity found. So we have seen that as well. But I would say that this is not unique. I mean, we test devices in other ranges. Frankly, security is getting better, but we've still got a fair way to go. So although we do find a lot of issues in smart meters, it's not that smart meters are particularly weak or anything. It's just that they have quite a hard problem. Security is very important for them. And we see the same sort of problems in other places as well. So hopefully that gives you a feel.
Great, thank you, Chris. Final question for the session then. Are there different approaches in addition to malformed input testing? I think, Tony, do you want to take that one?
I can take that one. So I mean, yes, there are different approaches. So it depends whether you mean, so one of the things that we've found people want to do with Protocrawler as a tool, it is add on functional tests that are based on the understanding of the protocol it has. So it's perhaps worth mentioning that. We emphasize the fuzz testing here, but you can also create suites of regression tests that are based more on functional test scenarios of sending valid messages or doing negative tests based on invalid sequences of messages and so forth. There are other types of, I mean, you can do other types of negative testing outside of fuzzing as well, of course. You can generate your own manually, but I think what, and if you do vulnerability scanning, for example, you're looking there for particular signatures of vulnerabilities, but these are all of known vulnerabilities, but these are all in other categories. Fuzzing goes into that area of the unknown more than any of those other approaches.
Great, thank you, Tony. We've made a note of all the questions and we can provide some follow-up answers in our follow-up materials as well. So sadly, we've run out of time today, but if we haven't been able to answer your questions, then we will provide responses. Thank you all for your time today. As mentioned, this is the first in a series of 3 webinars that Scital is running on fuzz testing smart meters. So if you would like to delve a bit deeper into the details of how to select the right fuzzing tool for you, make sure you sign up to our next session on Wednesday, the 3rd of May. We will share a recording of today's webinar with all our attendees in our follow-up communications, along with a link to register for the next event. If you do have any questions you'd like to put to the team following today's session, please get in touch with David using the contact details on screen now. Otherwise, we look forward to seeing you at the next webinar. Thank you very much, everyone.